Okay. Section 2.5 starts with substitution methods. One such method is to take a differential equation which is not linear and try to make it a linear differential equation. One of these types is the Bernoulli type differential equation, which has the form Bernoulli differential equation. Y prime plus P of x y equal to f of x y to the power n. Now, as you can see, if n is not 1 or is not 0, then this is not a linear differential equation. Our intention is to make it linear whatever n is. Here, P of x, f of x are both functions of x, and n is a number which is a real number. It could be positive, negative, and why not also 0. The intention is to solve this differential equation, which I will call it equation 1. The idea is to get y as a function of x. Okay. The following cases arise. Case 1, when n equals 1. Okay. Equation 3 becomes I mean 1, sorry. Equation 1 becomes, this is 1, okay. Becomes y prime plus P of x, y equal to f of x, y. This is clearly a linear homogeneous differential equation when you write it in the following manner: y prime plus P of x minus f of x, y equals 0. This is an equation which you have seen before, so I will not solve it here. The second situation, or the second case, is when n equals 1, n equals 0. Okay? The equation becomes, 1 becomes y prime plus P of x, y equal to just f of x. Okay? This is linear order 1, which you have seen before and can be handled. The most important case is case 3. Where we have n not belonging to the set 0, 1. It's not 0, it's not 1. At this point, let us start with an example. An example. differential equation y prime minus 2y equal to x y to the power 2. Call this equation 2. Is clearly of the Bernoulli type with p of x and f of x as minus 2 and x respectively, and n equal 2. Definitely different from 0 or 1. Division by y squared produces the differential equation of in the following form: y squared minus 2 over y equal to x, which I will call equation 3. Okay. Now observe. Just observe that the expression here, y prime over y squared, is nothing but minus 1 over y, all primed, which is equal to minus y to the power minus 1 prime. Now, the justification for this is that the derivative of 1 over y is, of course, minus 1 over y squared times y prime, using the chain rule. So it makes sense to take 1 over y as a new variable. You can call it v, w, u. I will call it z at this moment. And see what happens to our equation upon this substitution. Equation 3 now becomes as you can see, minus z minus 2 minus z prime minus 2z equal to x, or just z plus 2z prime plus 2z equal to minus x, which is, as you can see, linear of the first order. Linear first order. Okay. Now, of course, this type of equations you have seen earlier may need integration factors. In this specific case, an integration factor can be obtained by the usual method with integration factor mu equal to e to the power integral of p of x dx, with p of x as 2, this becomes e to the power integral of 2 dx, which is equal to just e to the power 2x, without referring to the constant of integration, which will be taken care of toward the end. Our equation becomes now, okay, now multiplying our last equation by this integrating factor, we end up with the equation z prime e to the 2x plus 2 e to the 2x z equal to minus x e to the 2x. Now, notice now that the left-hand side of this equation is nothing but z e to the 2x prime, okay? Which means that z e to the 2x can now be evaluated or can now be equated to minus x e to the 2x dx, okay, which upon integration by parts or by tabular integration will give you minus x over 2 plus 1 over 4 e to the 2x plus a constant, okay, from which we end up with z equal to, of course, just divide by e to the 2x minus x over 2 plus 1 over 4, just divide by e to the 2x plus c e to the minus 2x. Okay. But this is z. Our intention is to find y as a function of x. From this, now we can find our y to be 1 over this expression, 1 over z, which after simplification will give you 4 over 4c e to the power minus 2x minus 2x plus 1 as the solution to our Bernoulli differential equation. We now have solved one Bernoulli type differential equation. But this is just an example. Okay, now let's go to the general situation. What happens when we have the basic equation 1, which is Bernoulli of the Bernoulli type. Okay, now let's find out how we can do the general solution of this type of equations. To generalize, one, which is actually here, I will repeat it, y prime plus p of x y equal to f of x y to the power n. We start dividing as step 1, start dividing by y to the power n to get y prime over y to the n plus p of x y over y to the n equal to f of x. Again, notice that y prime over y to the n may be written as y to the power 1 minus n divided by 1 minus n prime. Again, using, of course, the chain rule. Now, this means that the substitution u equal, you can say hence, the substitution u equal y to the power 1 minus n is very sensible. Is sensible. Okay? And let us call this equation number 5 or number whatever, okay? 5. Okay? 5 becomes u prime over 1 minus n plus p of x u equal to f of x. Okay? Which, as you can see, is a differential equation of the linear type, first order, with u as a function of x. This is u, of course. Okay? U being the function that we should work upon. Multiplying this by 1 minus n, you get u prime plus 1 minus n p of x u equal to 1 minus n f of x. Now, this is the form in which we usually have the first order linear differential equation with modified p of x and modified f of x. Whereas in the linear differential equation of the first order, we have a p of x multiplied by the function. Over here we have this. So this is our p1 of x. And this is our, let's say, f1 of x. Okay? And this is now linear first order. Okay. Okay. It remains for us to solve this differential equation. And after you solve it, of course, just replace u by y to the power 1 minus n. Okay? And this will give you the solution of the differential equation.